Welcome everyone to the heat transfer section. At this moment we are going to solve an exercise related with convection and conduction. So we have in this exercise a house which has a composite wall of wood, fiberglass insulation and plasterboard as is indicated in this sketch. On a cold winter day, the convection heat transfer coefficients are alpha 0 equal to 60 watts per meter square Kelvin, which is the one that corresponds to this side, and alpha inside equal to 30 watts per meter square Kelvin. And the total wall surface area is 350 meters square. This is the inside side. We have the different widths of the layers that are in this wall, and we have to determine first is a symbolic expression for the total thermal resistance of the wall, including inside and outside convection effects for these conditions. Second, determine the total heat loss through the wall. Third, if the wind were blowing violently, raising the alpha outside to 300 watts per meter square Kelvin, we need to determine the percentage of increase in the heat loss. And last, we need to answer this question: what is the controlling resistance that determines the amount of heat flow through the wall? So the first thing we need to get the values of the conduction coefficients for for the different layers. We have this table that I found, but these are the conditions at 300 Kelvin, and we can make just an estimation of the temperature, which kind of temperature we are talking here about. So we have like the average temperature is equal to T0 plus T inside, T outside plus T inside, sorry, over 2, and this is equal to 20 grades centigrades minus 15 grades centigrades over 2, and this is equal to 2.5 grades centigrades. If we transform this to Kelvin, it gives us 275.5 Kelvin, and we have 300 Kelvin, so yeah, it's more or less 300. Yeah, it's near to 300 Kelvin, so we can use these conditions. So the conditions that we are looking for, so we have plasterboard, we have glass fiber here, yeah, the glass fiber, because they are giving us the density. We have plywood here, and we have yeah, this plasterboard here. Perfect. Okay, great. So this is like the problem that we have. So the first thing that we are going to determine to solve the first question, we need to determine a symbolic expression for the total thermal resistance of the wall. So the first thing that we are going to do is to make like kind of a sketch of the different resistances that are in this that are represented in this wall. So we have a resistance at this point. We have because this is the convection side here is flowing wind. We have resistance, the conduction here. We have the conduction here, and then we have another resistance here. So practically we have the first resistance, we can depict it as here. Then we have the second resistance, yeah. Then we have the third resistance, we can depict it very large, yes. The fourth resistance, and finally we have our last resistance. So we have one over alpha I times the area, the contact area. The second resistance is LP over lambda P times the area. The next one, LV lambda V area, LS over lambda S times area. And the final one is we have the convection in this at the outside, so it's 1 over alpha outside times the area. So as you can see, it's very straightforward when we already sketched the resistance in this way. So we define the total resistance as the sum of the individual resistances, and as we have in the electric circuits, we have a resistance in series, so that's why we define the total resistance as this, and this is equal to 1 over alpha I times area plus 1 over alpha 0 area. Once we got this expression, then we can replace the values to get our value of the total resistance. So this is 1 over then we got the result 9.52 plus 16.8 plus all of these multiplied by 10 to the minus 5 grade centigrades over watts, which gives a final result of 831 times 10 to the minus 5 grade centigrades over watt. With this result, then we just apply our equation to solve the heat transfer over this wall. So we have delta T over R tot, and this is delta T, which is the delta T is the one that we have the inside and the outside, which is T inside minus T outside. Why in this way? Because this side, the inside, is warmer than the outside, so we have a heat gradient that is in this direction. Yeah, this over R tot. And we replace the values. We got 20 minus 15. This is this is grade centigrades over R tot, which is the one that we just calculated, and to the minus 5 grade centigrades. And this at the end will give us a heat transfer of 4.21 watts. Done. Now the next question: if the wind were blowing violently, raising alpha outside to 300 watts per meter square Kelvin, we need to determine the percentage increase in the heat loss. To do that, we just need to say that alpha 0, that at the beginning was 60 watts per meter square Kelvin, just went to 300 watts per meter square. Yeah, probably the wind started to blow to speed up. So which consequence brings that we have this new value in our alpha 0, that our resistance at the outside, which is defined as alpha 0 times the area, will be equal to at the beginning was 4.76 times 10 to the minus 5 grade centigrades over watt, and after the convection coefficient increases, then we have a reduction in this resistance, since more heat can be transferred. Okay, then this value implies that our R tot will be, that at the beginning was 831 times 10 to the minus 5 grade centigrades over watts, then transits to 826 times 10 to the minus 5 grade centigrades per watt. We are going to call this R old, and then this one R new. So R new minus R old over R old times 100 will give us about minus 0.6% when we just replace these values into this equation. Our heat transfer rate will be equal to Q nu is equal to delta T over R nu, which when we replace the values will give us 4.237 kilowatts, which correspond to 0.6% of R old, an increase of 0.6% of R old. For a 5-fold decrease in resistance due to this increase in the wind velocity, this 0.6% is practicable, negligible. Yeah. This leads us to our final question. We need to answer which is the controlling resistance that determines the amount of heat flow through the wall. To solve that, then we need to go back to the expression that we developed for the total resistance and the values that we got here. From this set of values, the largest of this one, which means this expression here, which corresponds with our glass fiber blanket, our middle layer in the wall. When we do some calculations here, RB, which is the blanket that we have at the middle, over R tot will be equal to 752 over our total, which was 830, and this gives us more or less 90%, which means that this material layer controls the resistance of the wall. So that's it. So I hope that you can follow all the steps that leads to the solution of this exercise. And enjoy the exercises of the heat transfer section. Take care. Bye bye.